Chapter 5.4, Exponential Functions, Differentiation and Integration. Day 3, Integrate Natural Exponential Functions. You may remember from yesterday, we took y equals e to the x and took the derivative of that. And the derivative of e to the x happened to be e to the x. Well, today we're looking at it backwards. So today we're asking the question, what is the antiderivative of e to the x with respect to x? And if you remember, when we say antiderivative, we mean what function has e to the x as its derivative? Well, as you can see, the derivative, the function that has e to the x as its derivative is e to the x. You could also do e to the u du, which you'll see probably more often as you're doing substitution. That will also work out to e to the u plus a constant. It's a pretty simple and straightforward problem. The difficulties come when we add in the other concepts. We add in the substitution, the change of variables, the trapezoid rule, the fundamental theorem, the second fundamental theorem. And we're asking you to apply one concept to all these ideas we've had in the past. So let's practice a few of these. We'll start with just remembering these are our integration rules, theorem 5.12. All right, so we'll start with a pretty simple, straightforward. Antiderivative of e to the 3x plus 1 with respect to x. Now we need it to be e to a variable. We don't have an expression up there. So what we can do is we can substitute that expression out. Let's take it out and replace it with u. So then u would equal 3x plus 1. Du would be 3 dx. Notice we have the dx, we need the 3, so we'll put the 3 there. Balance that with a 1/3. So we got 1/3 times the antiderivative of e to the u du. Antiderivative of e to the u is e to the u plus a constant. And because it's with respect to x, we'll put our x back in. So it's 1/3 e to the 3x plus 1 plus a constant. Our next problem, very similar. We got e to the 1 over x. Let's rewrite that so we get rid of the fractions and have negative exponents instead. So this will be e to the x to the negative 1, and then x squared on the bottom will be x to the negative 2 dx. Or dx, sorry, not du. I said it right, wrote it wrong. Again, we need e to a single variable, not an expression. So we'll substitute that expression out. U is x to the negative 1. In that case, du is negative 1 x to the negative 2 dx. Notice we have x to the negative x. We're missing the negative 1. So I'll put in negative 1 and I'll factor it out to kind of keep it balanced. Multiply by negative 1 twice, you haven't done anything, which keeps it balanced. So we got negative antiderivative of e to the u. Right here is u. Right here is du. So negative antiderivative of e to the u du is negative e to the u plus a constant, but we need in terms of x. So we go negative e to the x to the negative 1 plus a constant. If you are insistent, you can rewrite it as 1 over x. All right. What do we do when there's trig there? All right. Is it really any different? It's still an expression. Substitute that expression out. U equals cosine of x. So du equals negative sine of x dx. We almost have negative sine of x. We're just missing the negative. So multiply by negative. We've changed the problem. Multiply by negative again to maintain the balance. So what we got is e to the u du. When we take the antiderivative, we got negative e to the u plus a constant. Substitute back in. We got negative e to the cosine of x plus a constant. All right, evaluate this integral, this definite integral. Right? As you look at this, we got a fraction. Right? We got an expression on the bottom of a fraction. Usually when there's an expression on the bottom of a fraction, you want to get rid of it. Substitute it out. So I'm going to say u is the denominator. 1 plus e to the x. Right? As I do that, then my du will be, well, the derivative of 1 is it's a constant, so it's 0. Derivative of e to the x is e to the x dx. Notice we have this right here. We got u on the bottom, so we can substitute it out. So it'll be du over u. We're going to have to change our limits. So we got, if we substitute 0 into our expression, 1 plus e to the 0. E to the 0 is 1. 1 plus 1 is 2. We substitute 1 into our expression. We got 1 plus e to the first is 1 plus e. And we'll integrate that. Du over u is natural log of u from 2 to 1 plus e. So we got the natural log of 1 plus e minus the natural log of 2. You can simplify that if you want. It doesn't really need to be a number. I may want to write it as one expression, 1 plus e over 2. But otherwise, it's fine. Right? Continuing our quest on these problems to kind of understand what's going on, take a look at this one. This one seems to be a whole lot of, mess. Whenever you got something like this, you just try substituting something out. And like we said in the past, it's going to be either the bottom or top. Look for a function, set a function. If you have fractions, look for bottom or top. I'd always start with the bottom. U equals e to the x plus e to the negative x. And as we take our derivative of u then, derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x times negative 1. All these will be with respect to x, all dx. And take a look how nice this works out. All right? That ends up being the top. So we got du up top, u on the bottom. Well, du over u, the antiderivative of that is the natural log of u plus a constant. Natural log of, in this case, our u is e to the x minus e to the negative x plus a constant. And notice I got rid of the absolute value signs there. I probably should not have. So I'll put those back in. Because it has to be positive. All right, as we continue, look at this one. This one is a nice problem. I like to do this type of problem because it's one where you overthink it, it's really going to mess with you, but if you keep it simple, it's not too bad. You got 3 things up top, 1 thing on the bottom. What we'll do is we'll split this into 3 different fractions. E to the 2x over e to the x plus 2 e to the x over e to the x plus 1 over e to the x dx. Now on each of these, we can reduce them. The first one reduces to e to the x. The second one reduces to 2. And the third one reduces to e to the negative x. And we can integrate each one of these. Notice I split those, integrating them separately. You can integrate a big one, or you can integrate it separately. It doesn't matter. Antiderivative of e to the x is e to the x. Antiderivative of 2 is 2x. Antiderivative of negative, or e to the negative x, we need that to just be u. If u is negative x, du is negative dx. So put our negative there. We'll balance it with a negative there. It'll really end up being negative e to the u du, which is e to the u. it'd be minus e to the u, but our u is negative x plus a constant. All right? I kind of didn't write out the work here. Eventually get to the point where you'll see that e to the negative x and you just switch the sign. Or you see e to the 2x, you'll divide by 2. All right? Finally, this one. This one absolutely stumps people until they just sit down and look at it and just apply properties algebraically. Apply your algebraic properties of a natural log. What you should notice is we can bring this out front because it's an exponent. So we can rewrite this as 2x minus 1 times the natural log of e. Well, the natural log of e, that's a fancy way of saying 1. So really we're saying 2x minus 1 times 1, which is really 2x minus 1 with respect to x, and that's x squared, power up, divide by 2, divide by the new power, x squared minus x plus a constant. That is a common trick they like to pull. Can you handle that? The answer is, yeah, pull that out, and natural log of e disappears. Right, so in conclusion, the antiderivative of e to the x, antiderivative of e to the x with respect to x, well, that's e to the x plus a constant. What function has e to the x as its derivative? Well, by golly, it's e to the x.